welcome to our computer architecture subject. Today we will talk about computer architecture introduction in this lesson. So what is computer architecture? It has to do with the internal design of a computer, including the hardware and the software that is needed to make the computer work. So the primary things we will be discussing is the processor or the central processing unit, the main memory, input-output devices, and secondary storage. All of these things comprise the internal parts of the computer and are subject to the computer architecture lessons. So let's look at some abstraction layers. What we have seen here are the physical devices that comprise the computer internally. If we are to look at this as an abstraction layer, we will see that those physical devices sit on the bottom. So we have physics and devices on the very bottom of the stack of the computer architecture. After that, we have circuits, gates, which are register transfer level. At register transfer level. After that, we have the instruction set architecture, or ISA. And these are already, so we are right here on the spike on the right side. We are crossing the line between hardware and software. So up until this spike right here, physics, devices, circuits, gates are all hardware devices. Once we go up the spike here into our layers, instruction set architecture, this is already software. Operating system is also a software, so are the virtual machines. Instruction set would be the basic instructions that a central processing unit's processor CPU executes, that are like basic mathematical arithmetic things. Add two numbers together, subtract one number from another number, load the contents of memory location into this address, save the result of your addition or subtraction into that address, jump from this instruction to the next instruction. Very simple things like this are part of the instruction set. The operating system sits on top of the hardware along with the CPU that executes the instruction set, which is pretty much machine level language or machine instructions. On top of that sits the operating system. The operating system controls the devices, the hardware, and CPU, memory, hard drives, input-output devices will be controlled by the operating system through drivers. So the drivers is the kernel level or kernel mode software. That's a very low level software that runs on the bare hardware over the devices, the CPU, the input output devices, keyboards, monitors, and other things of this nature. The memory, the buses, the operating system would control those devices via the drivers. The operating system has a basic logic of running applications on top of itself. and controlling those applications, providing them the resources, the CPU, the memory, the input output devices. Usually the operating system would schedule them, usually in a round robin fashion, to use the CPU and to so that each application will have a slice of time of the CPU to run. It also provides them memory space to where they can store its code or instructions, as well as its data, and to run and execute its code. So the operating system would manage all the applications that are running. They could be virtual machines which would run on top of the host operating system. Some virtual machines would run on the bare hardware, depending on if they're level 1 hypervisor or level 2 hypervisor. So once we have the operating system, on top of that, we could host applications. Also, programmers like ourselves, computer programmers, could write programs. This means they will create a new application that runs on the top of the operating system. An instance of a running application is called a process. That is when it gets the CPU, it gets memory to run, it gets to its instructions getting executed, and so on. That is what the operating system would manage in this round robin fashion. These things are called processes. So by using the programming language, the programmer would create applications that would be run by the application system in form of a process. The algorithm would be a basic logic that allows our application to come to life, or it implements our intentions, desires, creativities for what we would like to create in this application, will be implemented through the algorithm logic. So this is overall how a computer looks like. That's the basic computer architecture abstraction layers. Okay, so let's look at the computer architecture in terms of design and analysis. Architecture, if we are going to be designing, let's say we want to design this. We want to design a new computer with a new architecture, with a new operating system, with new applications running on it, with new algorithms. How are we going to proceed with this? So it's an iterative process. First, we will search the space of possible designs at all levels of the computer system. This is what is shown here. All the possibilities are in this tree, and we would run a particular path to find the right design for ourselves. And then where it comes to us of being creative, what we would like to create. Do we want to create a new hardware, a new CPU, a new memory, a new operating system, or a new application? So it comes up to our creativity in design. After that, we of course need to take into consideration the cost of what it will cost us to implement this new creation of ours, and do some performance analysis. Is it running properly? Why are we creating this new operating system? Is it any better than the previous operating system? Is it faster? Is it cheaper? Is it performing better? Or what are its advantages of the new system that we are creating? So we will do some performance analysis, and to separate the good ideas from other ideas that may not be bear any fruit for us. So we have design and analysis that come together, that need to be performed for the new architecture design. So applications suggest how to improve technology and provide revenue to fund the development. we would want to create new technologies if they are improved better or serve a new purpose. For example, that's a new technology that was not existing before, or it is a technology that improves the previously existing technologies. That is just a new and better improved version of them. So we have applications and technology, as we can see, that flow into one another in a circle. So they keep going back and forth in between each other. When we are creating new versions of applications, we need to take into consideration the compatibility. So we need to allow backwards compatibility for the new applications that we are creating. Another consideration is the cost of the software development. In order to make this compatibility possible, compatibility is essential for the market, so it's a major force in the market. Here we can see trends of the processors and the central processing unit. We can see trends of how the CPU technology is developed through time, going all the way back to 1978, and through the years here we can see the new CPU names along with their speeds, hardware and software are shown here. So back, the oldest ones were called VAX, VAX, then we had Sun, then we had MIPS, MIPS, then we had Alpha, and now we have Intel Pentium, and AMD CPUs. And as you can see, the idea is that the next or the newest technology, it's going to be better or faster or cheaper or in some way of a better advantage to the user than the previous version. So let's just think about wisdom for a moment. Why are we creating these new technologies? We just mentioned because we want to have some advantage to the user, whether that is a faster processor, a cheaper processor, a higher performing processor, that is somehow to a better advantage to the user than the previous processor or previous version of the technology that we are developing. So here are some conventional wisdoms. Here's the first wisdom. Power is free. Transistors are expensive. Here is new wisdom here. Power is expensive. Transistors are free. So things change. So we need to go with the flow, so to speak, with whatever is currently the trend and whatever is the current wisdom and the current law for the costs of the technologies, as well as the powers of the technologies, as well as the solutions and the benefits that they provide to the user. So we have some new conventional wisdoms and old conventional wisdoms. For example, multipliers are slow, memory access is fast. When we are designing the new technologies, we need to keep this kind of wisdoms in mind and take them into consideration for our new technology design. Okay, so here is a nice visualization. We have seen the layers earlier here up to the spike. This was all hardware, physics devices, circuits, gates, and registers. And on top runs the software instruction set, operating system, applications, programming languages. Here is a nice visualization. The hardware is on the bottom here. This guy is the hardware. The hardware holds the instruction set. On the top of the instruction set come the developers and the users who are having a better time than the guy on the bottom who holds the hardware. Why? Because this guy is set in hardware. He is not going to be creative or changed or have any flexibility. These guys that are shown as running around and dancing and being more free looking because we as the developers can implement these guys to be whatever we want them to be. So imagine these are new applications that we are coding, programming, or implementing, and we can implement them to be whatever we want them to be. So they can be created now or changed later. And that's why they're called software, because they can be changed at our choosing, at the discretion of the programmer. The hardware can also be changed, but it's not so easy. Hardware is hard to change. That's why it's called hardware. That once the hardware is there on the machine, it sits there until we trash it and get a new hardware. While the software could run on top of the hardware and be changed at any time at our will, at the discretion of the programmer. Okay, so let's look at properties of good abstraction. It lasts through many generations, so it has portability. It can be used in different ways, so it has generality. It's general. Provides convenient functionality to higher levels, so it is convenient. And permits efficient implementation at lower levels, so it is also efficient. So this right here is the abstraction, and these are the properties of a good abstraction. Okay, so the old definition of computer architecture is instruction set design. The instruction set only deals with, as we just mentioned, the simple machine level instructions that the CPU is running, such as simple arithmetic, adding two numbers together, subtracting two numbers together, loading a number from a particular memory location into a register, writing the results of the addition and subtraction into another register, moving the contents from the register back to the memory, jumping from one memory address to another where the next instruction is to be executed, and things of this nature. This is what the CPU is doing all day long. So this is called the instruction set of the processor. The old definition of computer architecture had to do with defining the instruction set for the processor and designing a better instruction set. Other aspects of the design are the implementation of, okay, we have a good idea of a new technology, of a new instruction set, of a new architecture. Now it's time to bring it to life and make it implemented, make it real. So the job of the architect, it's actually includes much more than the instruction set design, because we have seen an entire stack here of abstraction layers of the computer architecture. So the designer of the architecture could be working at any of those levels. Instruction set is only one level here, as we can see. So what matters is the functioning of the complete system with all of the layers that we have seen there. Hardware, compiler, operating system, applications that run on top of it. So the computer architecture would focus on design techniques, machine structures, technology factors, evaluation methods, and all of these things would determine the new computers that are coming up in the coming century. So, computer architecture includes computer organization, as well as the hardware and the software and the boundary in between them. Computer architecture involves all of these concepts. The operating system, the applications, programming languages, user interface design, compilers, as well as any new technologies that are necessary to make the new architecture possible, as well as something called parallelism. What is parallelism? So we just mentioned that the CPU, what it was doing all day long was this: running the instructions. The simple instructions: add, subtract, load from memory location, jump into another memory location, things of this nature. Now, notice one CPU can only do one thing at a time. He can run the add instruction. Next, he can load the result from the add instruction into a particular register. Next, move the contents of the register into the memory. Next, jump to the address of the next instruction. So it is sequentially executing each instruction one by one, line by line. Kind of like when we are reading a book. You read the first line, go to the next line, go to the next line. To read the entire book, you would have to read every single line in order. So this is what one CPU with one core can do. Now, if we want the CPU to be doing two things at the same time, he can't really do that. CPU can do one thing at a time. So if we want to run two applications at the same time, guess what? The operating system is going to divide the CPU time amongst all the applications that want to run. So it's going to create a process for each application. It will give it memory space. It will load its instructions into the memory that is to be executed. It will load its data into another part of the memory. And then give it a fraction of the time of the CPU. So the CPU for an instant of time will run one application. In the next instant of time will run the next application, and in the next instant of time will run the third application. Really, he's running one thing at a time. And they are coming around and back to it in a round robin fashion. Each application is gonna have the CPU for a fraction of a time. They look like they are running at the same time because they run for such a small fraction of time that human being cannot tell when they're switching. But in reality, the CPU is only doing one thing at a time, is running one instruction, is running one application, and then goes to the next. Now, if we want to be smart and want to actually run two applications at the same time, we either need to have two cores into the CPU, or we need to have two CPUs, or we need to have a code that is programmed so that two instructions can run at the same time. Because the logic, the algorithm, where did we go with this algorithm? The algorithm, the logic of our code, it requires you first add the two numbers together. You need to have the result of those two numbers before you go to the next instruction, which loads the result from the register into the memory. You can't load the result into the memory before the result was calculated. You see, those two can't run at the same time. First, you need to add the numbers, produce the result, and then load this result into the memory. You can't load the result until the result has been produced. So that's why parallelism is tricky. We want to run two things at the same time, but the second thing is not ready to run because it expects the result from the first thing. So parallelism is quite tricky. We could design our code very carefully to where two instructions can be ran at the same time. In this case, if we have a CPU with multiple cores, it can run one application on both cores. This is very tricky. Or it's just gonna run one application on one core, another application, another core, and run them sequentially as they were originally designed. So these are the two forms of parallelism that are possible. So let's look at overall the topics for the computer architecture. Simple machine design, instruction set design, microprogramming, unipipeline machines, and simple pipelines. Memory hierarchy, types of memories that exist, random access memories, caches, and optimizations for those memories, virtual memory systems, as well as the rest of the memory that is not a part of the main memory but is in hard drives, external memories, as well as exceptions and interrupts in terms of running our instructions. They can be interrupted if needed, if some higher priority process is happening. The currently running process can be interrupted. For example, let's say all the cars are running on the highway, on the interstate. They run in the order that they're coming. All of a sudden, there comes an ambulance with the red lights on, with their sounds, with their sirens. The ambulance has got life-threatening emergency. It needs to go through the rest of the cars, and all of them move to the side and make way for the ambulance to pass through. This means some high priority process is happening and it's coming, and the other ones need to move to the side and let it run. So these interrupts would happen in that situation. Okay, so then we have complex pipelining. Explicitly parallel processors like the ones we have discussed. How are these applications going to run in parallel? Is the application programmed to be run in parallel? Or are we going to run two separate applications in two separate cores or two separate processors in parallel? What do we mean by parallel? So, all of these things are topics that we will be studying in this in our lessons of the computer architecture subject. Okay, instruction sets, pipelines, main memories, virtual memories, exceptions, and interrupts, as well as the parallel processors, which are actually an advanced subject. And then the processor architectures. Memory models, cache coherence, and synchronization. So, for this course, this is a graduate computer architecture course. In order to cope with the course or with the subjects, the prerequisites, which means a student who is a graduate student or a master student needs to have taken an undergrad course in computer architecture. And if they didn't take this course, or if they have forgotten the course and the contents, or if graduate student came from another major or from another discipline, then please review the appendices in our textbook. Review the appendix A, B, and C in the textbook so that you can refresh your memory on these important subjects. The subjects are instruction set, data path, pipeline, and memory hierarchy. You can once again find these subjects in the appendix A, B, and C from the textbook. Other things about graduate studies is that graduate students are researchers. So we would be studying some research papers. An important skill to have here is for the students to be able to work with research papers, rapidly read, scan, understand, and learn from the papers. In these, being able to read and scan the research papers and assess the papers, the new technologies they're suggesting, the algorithms they're using, what results they accomplished, how are they improving the previous technologies. All these skills are understanding what the papers are proposing or what is the value contribution of these research papers is key to the successful graduate students. So we to measure performance of the computer architectures, we would look at technology trends and we will do some performance evaluations, how the technologies changed through the years and how is the new one better than the previous one, including our textbook. This is how our textbook computer architecture looked back in 30 years ago, and then the new versions, every couple of years it will have a new version. So that was the first one back in 1996, another one came 2002, edition, next edition was in 2009, next edition 2011. So you can see how the new technologies are coming up and what is changes are happening into the textbook. So back in 2009 there was a shift to multi-core processors. there was reduced emphasis on the instruction level parallelism, and there was introduced a thread level parallelism. In the next version, 2011, the instruction level parallelism was reduced to a single chapter. More attention was given on requests data, thread level instruction, as well as the moving from CPUs to GPUs. What are GPUs? They will allow for massive parallel processing, as they will have many cores. Also, the subjects of cloud computing, smartphones, and tablets was introduced into this next version, and there we have the newest version of the book. So you can see even the textbook is going through its own evolution. This is the first microprocessor that was designed. It was called Intel 4004, and that was in year 1971. It was a 4-bit computer. It had a 4-bit accumulator architecture, and it had 2,300 transistors, 750 kilohertz clock, and it was running 8 to 16 cycles. And this is how it looked like. So we can see all the way back kind of the history of the microprocessors. IBM was a big contributor to many of those processors. So team from IBM was building personal computer prototypes back in 1979. Motorola project 6880 was chosen initially. The first 8-bit bus version was called 8088. As you can see here, we have 4 bits, so that was 4004. And the 8-bit is called 8088. Nearly 250,000 was sold, and later really 100,000 were sold. You can see this computer was quite huge. It needed to be carried with 2 tractor trailers. It was weighted 12 tons plus 8 tons, and it was built for the army, for the signals of the U.S. Army Corps. Okay, so today we had some brief introduction to computer architecture. We have seen the main parts of the computer architecture, the main hardware and software parts, as well as how it is changing through time. We are always looking to improve the new technologies versus the previous technologies. Typically, human beings want to see a faster computer or faster processor. So we kept adding more and more chips to increase the speed from the previous versions of the technology. We also mentioned the concept of parallelism and the types of parallelism that exist. The parallelism can be implemented within the code. That would be instruction level parallelism, or they could be running multiple applications at multiple cores or at multiple CPUs. Also, thread level parallelism we will study as well. So that is all that we have today for our lesson on computer architecture. Thanks for joining us.